Today it's my pleasure to introduce my newest friend and coolest new neighbor to Shorewood, Michelle Thaller. Dr. Thaller grew up in Waukesha and she made her way to Harvard, where she did pretty well. She at first was a little overwhelmed by some of her science courses, but then she found out that sooner or later the curiosity, passion, and kindness, not to mention the humor of her astronomer professors, made her feel welcome. She wanted to be around people like that. Good thing she was at Harvard. After getting her doctorate at Georgia State, Michelle took her postdoctorate research position at Caltech, and that led to a senior scientist position at NASA's Jet Propulsion Laboratory. In 2009, she transferred to Goddard, which is the NASA base for flights in Washington, D.C. And then, forgive me, I'm reading disjointed. She became very interested in how science was communicated to us, the public, not just to the scientists, and decided to specialize this as the rest of her career. You might recognize her from NASA broadcasts, such as the launch of the James Webb Space Telescope and many other events. She's appeared on behalf of NASA on television screens across the country on shows like How the Universe Works, Nova, The Universe, Nat Geo, and Days of Our Lives. Michelle has received multiple awards for online science content and is especially proud of the social media program at NASA. Currently, she's working for the Smithsonian Institute as an adult educator and with its travel programs. She's hugely honored to be with us today, but it is really our honor to welcome you, Shorewood's newest neighbor, Dr. Michelle Thaller.
Oh, well, it's wonderful to be here. Wow, so many great people. It's a pleasure to be back in Milwaukee. I left Wisconsin in 1988 when I graduated from Waukesha South High School, and I all my life wanted to make it back here. I've lived all around the world, and the community and the quality of life and the quality of, I mean, growing up here with the parks, the museums, the restaurants, everything. This to me is the best city to live in that I know in the world. And I'm incredibly happy to be back. So I've gotten, let me just start my presentation here. I've gotten so many questions about where I live. So everyone's like, where do you live in Shorewood? So if you go to the intersection of Lake and Capitol, and you just sort of look west from there, away from the lake, you'll see this old prairie house, which was built by Russell Barr Williamson. And he was one of the major project managers that worked with Frank Lloyd Wright. So yes, that's my house. Please come in. Please say hello. I get more people than you'd think. Just walk up to the house and say, "This looks like an interesting house," and I say, "Come on in," and come and enjoy the architecture. Come and enjoy the history of Shorewood. So I've got a sister in Bayview. My mom lives on Prospect in the Landmark, and my dad lives in Pewaukee. So it's really nice to be back here with my family. So that said, we're going to do something a little bit different today. It's probably not all that often you get a chance to have some astronomy and some science, and to do that in half an hour, which is always kind of torture for me because there's so much to talk about. So my degree in my research was as an astrophysicist that studies the life cycles of stars. And I still do that to some extent, but as my wonderful introducer said, when I was a postdoc at Caltech, which, by the way, in the same position that Sheldon is in the Big Bang Theory, I was a postdoc in astrophysics at Caltech, and it's a whole conversation. Invite me over for a glass of wine as to how that show was right and wrong in its portrayal of us astrophysicists at Caltech. But it was really a lot of fun. But I got quite interested in how science was communicated. And I spent the next 26 years at NASA trying to improve the way we communicate and have a larger audience. And I'm happy to say that, especially the social media that we do has close to 1 billion followers now across the planet. And for us, a successful media campaign, which involved scientific papers, press releases, animations, social media strategy as to when the timing would come out on all the different platforms. We were looking for engagements in the billions. And so that's something that I've really enjoyed, is figuring out how to do that. So for those of you that don't know a little bit of the landscape of NASA, This is an aerial picture of about a third of Goddard Space Flight Center, which was I was the assistant director of science for Goddard Space Flight Center. My specialty, there were several people. There was an assistant director of science for new business, or an assistant director of science for legislative affairs, and I was the assistant director of science for communications. And so I was in charge of the communications, where I'll give you a sense about how many missions later. But this is about a third. It's about a 10,000 person base. It's right on the outskirts of Washington, D.C. I also did a 3-year stint at NASA headquarters, learning more of the budget and the political aspect of working for the government. So I just retired in October. Things are chaotic at NASA right now, and that certainly won't be the focus of my talk, but I welcome questions about what's going on, about how I feel about it, and so, as I said, that won't be the focus, but it's been a very tumultuous time, and quite honestly, a frightening time at NASA. So that's about a third of the base. So this next chart I call a shock and awe chart. Don't even try to read it. But this is how many missions we manage at Goddard Space Flight Center. The missions are all acronyms. One of the things I found out at NASA is if you don't know an acronym, you're sitting next to somebody at a seminar and you say, "What does that acronym mean?" More than likely, that person will look at you and say, "I don't know either." So we try to we don't even know our own acronyms, all of them. But each one of those acronyms is a mission. That means a science team, engineering teams, a spacecraft, people that are doing communication, people that are doing international affairs, legislative affairs. They're grouped according to, this is actually the way NASA science is organized. We have an Earth Science Division, what we call heliophysics, the study of the sun. All those missions you see around the image of the sun there are planetary science missions. And then way up in the left-hand corner, astrophysics, stuff that's way beyond the Earth. So as you can see, the majority of the science investment at NASA is in Earth science, by far. And we operate, this is about 110 active missions. Some of them are being developed, some of them are running right now, some of them are being archived, but about 110 missions that changes every day when a new one starts or something ends. And the science budget at NASA is about $5.5 billion. And considering that we build the weather satellites, we build things that monitor the health of the Earth. Here in Wisconsin, for example, people that are running combines, that are harvesting their crops out in the fields, are doing so with information programmed right into the combine location with GPS from the Landsat satellites and from the satellites that we have monitoring crop health, moisture, soil, precipitation all over the world. So a little bit about what we do. It's not just all astronauts. I have many friends who are astronauts, and they are wonderful. And I just had my friend Sonny Williams come back from the space station, about 10 days ago now. So a wonderful thing. Just a little bit about that Earth Science program. This is an animation of all of the satellites we have that are doing original research about what's going on with the health of our oceans, our plant life, our atmosphere. This does not even include the weather satellite system that NASA builds, but then delivers to NOAA, the Weather and Atmospheric Agency, to operate. So most of the weather satellites, it's called the GOES series, they're built at Goddard where I worked. And then, as I said, yeah, we do the data for that and all the engineering, and then NOAA operates them. So, at any given time, we are looking at the entire planet. And of course, the wonderful thing about looking at it from space is that this isn't just a single nation or a border. Most of these missions are international collaborations. And all of the data from these missions is as soon as we can get it out, immediately and freely available to anybody on the planet. I've hosted visitors from all over the world, and they would look at our precipitation data. Every 30 minutes, we put out a data product, all the precipitation all over the world. And they were like, wow, how do we get this data? And I showed them the website. And they were like, do we need to sign a treaty? Do we need to sign an agreement? And like, the website. This data is all public and all free. And this is something that the United States does that I am extremely proud of. We have saved millions of lives. We have, we have a whole department of food security, figuring out how to get food to people who don't have just simply the transportation necessary, all of that. This gives you an idea. What this is, and I'll explain, is that this is a real-time simulation we did of all the data we take with these fleets of satellites of the Earth. You see all of these little dots, and you see some of the dots are kind of in squares, sort of sweeping over the Earth. Those are all the places where our satellites are observing. Most of these satellites go around the Earth about every 90 minutes. And so they're taking that data. Every once in a while, you see a big orange blob appear. And those are from our weather satellites, which are farther out and actually see the entire planet at a time, and then download a huge amount of data as to what a whole half of the Earth is doing at a time. At Goddard Space Flight Center, we have one of the fastest computers in the world, and we input about 1.5 million real observations every hour. From our satellite system, you actually see that there are the tracks of aircraft, mainly going over the United States, but in some parts of the world as well. Aircraft data, ship data, and then there's lots of little blue dots which show you all of the ground stations that we actually input data in every single hour. So, we monitor the planet. We find out what's going on. And then this is kind of lovely. I mean, so when you have all that data coming in and you run it through your amazing supercomputer, you're able to see the entire Earth working as a system. So these are real observations that have been color-coded to show you things that are in our atmosphere. The yellow is dust. You can see dust coming off the Sahara Desert, going all the way over the Atlantic. It actually helps make our soil more fertile in the Americas and even in the Amazon basin. The orange is burning carbon. So where you see fires, you see a lot of agricultural fires in the Amazon and in Africa. And if you want to, you can just kind of keep an eye on poor Australia. Australia has been having a lot of trouble with brush fires. And you'll watch the carbon coming from these burning fires literally be transported around the world. Pink is nitrate, which comes from pollution. That's a good pollution marker, as is the green sulfate. So those are all the different things lofted into our atmosphere. So we see the Earth as this incredibly beautiful, complicated, connected system. The behavior of the ocean affects the way the winds work. That affects the way the land is, the temperature of the land, the health of the crops. It's amazing to see the whole world working as a system. So as I said, the only nation in the world that provides this view of our planet is the United States and our science program. And for a $5.5 billion a year investment, I mean, I've never seen an agency work more efficiently than this. I'm very, very proud of my 27-year career at NASA and the people that I've worked with. And so, these sorts of accomplishments, I think, are incredibly inspiring. Now, I'm going to sort of diverge now into some of the stuff that I also find is inspiring on a larger scale. And I think that's important, too. What we do at NASA does have a lot of direct applications, technologically and earth science-wise. But then there's the things that show us the connection. And I want to really thank the person that gave the invocation today about how science can help us, really have respect for each other and for the truth and for our communities. So I'm going to start with something you all know very well and is actually an incredible thing to study, and that's the sun. So let me just start this video. I see it's either, okay, so can I do this and that? Thank you. What you're going to see. But the sun routinely throws off trillions of tons of hot gas at us and anything else in the solar system. And for the last couple of years, it's been particularly active. We're at something called solar maximum right now. This is another observation where they blocked out the light from the sun so you can see all of this material that comes toward us and anywhere else in the solar system. The most benign aspect of this is that this is what creates the northern and southern lights. These blasts of very hot gas, these high energy atoms, hydrogen and helium, get into our magnetic field near the poles. And just like a neon light, they actually cause the gases in our atmosphere to light up. The less benign part of this is that if there's a giant explosion on the sun like this happens routinely. If there's one that's particularly strong, it could actually affect our electrical grids, our electrical system. We are actually very biologically safe from this. It's not something that will kill humanity or anything. But in 1859, there was an explosion on the sun so extreme that it actually had the telegraph wires. At that point, the height of our technology were telegraph wires. They actually caught fire that day because of the electric current being forced through by all of these particles from the sun. So we deliver forecasts called space weather about what the sun is throwing out at us all the time. And that's another thing that's a big international effort at NASA. But again, going a little bit away from the practical and more into some of the inspirational, I think most of you know that the sun is a star. When you look at the stars in the night sky, these are things very much like the sun, but just so far away, they appear that small. The sun is our nearest star. And it's been one of my real pleasures as a scientist to sort of trace the way the stars live and die and figure out where we fit in personally to that question. So this is a picture from actually one of the beautiful ground-based telescopes. I've worked at most of the major observatories around the world, the ones in South America, and Hawaii, Australia, and South Africa. And this is a picture of a giant cloud of dust and gas that has stars being born inside it. And of course, we believe that about 5 billion years ago, our star would have formed in a similar cloud to this. We don't know where our cloud is now because once stars light up inside these clouds, their heat and these winds of particles, all those big explosions coming off the stars, tend to just blow these clouds away. The dark material of the clouds is actually made of dust, which is largely very similar to the dust you see in this room. It's made of carbon. It's made of carbon molecules. It's made of silicon. It's made of all those kind of dark, iron and gold and silver, a little bit of all of those heavier elements that we find. Predominantly carbon, actually. The stuff that makes up our chemistry, carbon atoms, that's what we call organic chemistry, chemistry based on carbon atoms, is very common in these clouds that actually give birth to stars. Now, stars form in a very simple way. All you need is gravity. That's it. If one part of this cloud gets a little denser than another part of the cloud, then that little denser part has more mass, and gravity attracts things with mass. And so as a little bit of a clump grows, gravity will bring more material to it, and then this cloud is so huge, it's actually, in this case, many dozens of light years across. And I'll define that. A light year is the distance light travels in 1 year. Light going 186,000 miles per second will cover about 6 trillion miles. And this cloud is hundreds of light years across. And you can see some areas inside that look kind of interesting and dusty. Now, at the very center of the image, there's sort of a dusty, dark cloud that, if you look very closely, has almost sort of columns or sort of finger-like structures to it. And if we sort of hone in on that, this is a picture from the Hubble Space Telescope. And a lot of you may have seen this. This is one of the more famous pictures. Has anybody seen this image before? Yeah, a few people have. Good. This was one of my favorite images ever taken by the Hubble Space Telescope. And what you're looking at is up close. You're looking at a nursery of stars. So to give you a sense of scale, the larger finger of this cloud on the left-hand side, from top to bottom, is about 5 light years long. So 5 times 6 trillion miles, about 30 trillion miles across. And to give you a sense about how big that is, in our local system, the nearest star to us in the night sky, not the sun, but the next nearest star, is about 4 light years away. So this cloud is so big, it would fill all of the space between us and the nearest star to us. And so when you think about a part of the cloud becoming denser and gravity bringing things in, there's a lot of material, trillions and trillions of miles. And finally, gravity brings so much material together that you make a star, just by gravity. Crushing all of those gases and the dust together. When you crush a gas together, the temperature goes up. And in the very heart of one of these collapsing clouds, the temperature gets to be tens of millions of degrees and sets off a natural nuclear fusion reaction. And that's what makes a star shine. So that is sort of star formation caught in action. Now, we suspect that we are related very closely to this process, the way the Earth started, the way we started. One of the missions that I had the honor of working on was the recently launched, I guess it's been about 2.5 years now, the James Webb Space Telescope. And this was built at Goddard. I got to actually look into this clean room. They never let me in. The only people actually let in were people that were actually building the telescope. And as you can see, they're all in these clean suits that cover them from head to foot, so they don't get any skin cells or any little bit of hair, any little bit of dust on the electronics. This room is hundreds of times cleaner than an operating room in a hospital. And the telescope mirror that you see there is about 20 feet across. It's made in segments, and we'll talk about why. And you can see people there making it. It was just incredible to spend my lunch hours, like you bring your sandwich, look in the window of that room, and watch them make that telescope. And then Christmas Day, 2.5 years ago, we launched this from the European launch site, which is in French Guiana in South America. And I just want to show you a little bit of that launch and talk a bit about the incredible engineering. The reason the mirror is in segments is that we do not have a rocket right now large enough, capable to launch that big of an object at once, a 20-foot telescope. And so the telescope had to be designed to be folded up like origami. And to make things launchable into space, they need to be as light as they possibly can be. So there's no such thing as a backup system. Everything has one chance to unfold properly. There were over 300 commands we had to issue to have little pulleys pull, or little wires stretch, or little actuators release something, and each one of those was a single point failure. There were no backups. That makes it too heavy. You have to make it as light as you can to launch. And so over the course of months, we had to bit by bit pick apart this telescope and see if it was going to work. So come along with me for the launch for a moment. For those of you that saw me on television, I was the NASA host for this. It was incredible, and everything went wrong during the broadcast that possibly could have. Our media feeds cut out. At one point, we were supposed to have a scientist give a remote talk, and that cut out, so I grabbed a scientist near me and said, hey, let's talk about this. So it was a terrifying moment for me. We're going up the 10 stories now of the Ariane 5 rocket, the largest rocket at the moment in the world. And at the very top, there is another clean room. Like I said, hundreds of times cleaner than an operating room. And here we put the giant telescope on top of this rocket, at the very, very top of the rocket. And then we're going to put the nose cone around it and launch it into space. Ariane 5. It was a day of thunderstorms, and we were very scared we were not going to be able to get off the ground. It was Christmas morning. We were also afraid all the French were going to go on holiday. Seriously.
And we have engine start. And liftoff. Decollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe.
What you'll see here eventually is some real footage from the rocket. That's the telescope being detached. And we're sending it out far away from the Earth, about 1 million miles away. It's about 4 times the distance to the moon, where it sits in space, and gives us an entirely new view, the best view ever of the universe. And it's now just rewriting the textbooks as to what we know about the life and death of stars, the Big Bang, everything in between. So there's the solar panels deploying, and off it goes. Incredible moment. And now came the 2 months of making sure it worked. But it did. So I showed you this picture from the Hubble Space Telescope, and it shows you a little bit about what we are doing as far as improving our view. This is Hubble, and now I'm going to show you the same part of the sky, the same cloud, with the James Webb. So, all of these stars were there, but they just were not available for us to see with the telescopes of the past. We needed something that was more sensitive. And so you can I just going to pan between those. And the telescope also has the ability to look inside these clouds. It's actually able to read the heat coming out of the warm parts of the cloud where the stars are forming. So there's just some lovely pictures of looking sort of closer into those pillars, each of those trillions of miles across. And where you see the red areas, we're gazing inside to see where stars are forming right now. These are real images. These were not doctored. This is real data. In some cases, we adjusted the colors to bring out different details, but we never invented anything. We never did a little Photoshop here. I mean, it's not like that. This is really what the universe looks like when you look at these star-forming regions with the best telescopes in the world. And now we can actually peer inside these clouds to see the very moment that solar systems begin. This is a recent picture. It's only a couple months old from Webb, and I'll explain what it is. This is what a baby solar system looks like. The dark band you see going through the middle is a band of dust, silicates, carbon, everything that you can make life out of, and it's actually obscuring a young star inside. The young star has just turned on its nuclear reactions, and the jets that you see going vertically, the red lines going up and down from that, are jets that come out when the nuclear reactions just begin for a star. So this is the birth of a star, and that disk of dust around it is just leftover stuff from bringing in all this material falling in from the cloud. It began to spin around the young star and form a disk. And you might not be so surprised to know that that's where our solar system and planets will eventually come from. This is an artist's conception, but what's going on in that disk right now is that all of that dust and material attracted by the gravity of the young star is beginning to form planets. And that's how we began 5 billion years ago. The amazing thing is we are now able to start sampling what that disk was like and what the chemistry was like, what we were built of before the Earth formed, before the sun had actually calmed down, and before any of this was here. So a little bit about that. This is a picture from the Hubble Space Telescope of a galaxy. And a lot of you have heard the word, and you probably may know that we live in a galaxy called the Milky Way galaxy. But personally, I don't think people understand just how dramatic a galaxy is. It's an easy word to say, but a galaxy is a family of hundreds of billions of stars that are all rotating around together. We are actually rotating around a giant black hole, about 4 million times the mass of the sun. You're going around that at about 500,000 miles right now, 500,000 miles an hour. And if you see all of that dust and debris, those are the clouds that stars form out of, all that dark material swirling around. The scale of a galaxy is really hard to imagine. A galaxy like this, and our own galaxy, about 100,000 light years across. So even traveling at the speed of light, the fastest speed possible, it would take 100,000 years to travel across our one galaxy. And to give you a sense of how big the sun is, the sun, of course, is so big you can fit 1 million Earths inside it. We talked about that. But the scale here, if we made the sun the scale of the dot of an I on a regular paperback book, think about the dot of an I on a page. If the sun were that scale, this galaxy would be a little bigger than the Earth. So galaxies are vast, and they're huge, and we are traveling around them. This is a picture from the Hubble Space Telescope. And what you can see are these beautiful lanes of dark dust, again, trillions of miles across. And everywhere you see a red kind of glowing area, that's a cloud that's forming stars right now. At 500,000 miles an hour, we move in and out of these spiral arms continuously. In the history of the Earth, we've been around the galaxy about 20 times, going about 500,000 miles an hour. And we pick up material as we fly in and out of those clouds constantly. We estimate about 100 tons a day. And some of that material is in big chunks, like meteorites, the rocks that fall to the Earth, and some of it is in little small dust grains. But we're constantly being enriched by this wonderful chemistry from the stars. Here's a picture from the Webb telescope of the same galaxy. And with the Webb telescope, we can bring out how beautiful all of those clouds are connected. It's not just one cloud that's forming stars, but an underlying scaffolding of dust and chemistry and beauty. And we're going around that, as I said, 500,000 miles an hour, but it takes 250,000,000 years for us to get around once. And what is in that dust turns out to be something quite amazing. So at Goddard, I was proud to do communications for our astrobiology group. If that's not the coolest word you've heard today, astrobiology, the chemistry of the dust between the stars. And here we have some of our incredible scientists holding up tiny little samples of this dust that we found. What this really is the building blocks of life and the question about how do they come to Earth and how do they end up being inside of us. So you find it often in meteorites. Meteorites are a sampling of this material that you find out in space. In fact, one of the places that we look for meteorites, because they're so scientifically valuable, a sample of our origins before they became planets, before they became people and creatures. A great place to look for them actually is Antarctica, because in Antarctica you have a huge glaciated area where the nearest ground or rock is under 2 kilometers of ice. And so we have people going around on snowmobiles down in Antarctica, and sometimes they find a rock from space. And as you can see here, they get very, very excited about that. This rock contains the information about what chemistry was like before the Earth modified it. We have rain and plate tectonics and volcanoes and wind, and there are so many things modifying the chemistry and the content of our planet. But this rock has been in deep freeze in space for billions of years, an actual sample of what our cloud was made of where we came from, of what was there that was available to make life. So again, my friends, the astrobiologists, this was a very dramatic picture of them taken for the cover of Nature magazine. We never have dramatic lighting in laboratories. I mean, there wouldn't be enough light to do your experiment. So you can see down at the bottom, that's actually what they look like. We were starting to find in these rocks from space, interestingly enough, the exact building blocks of our DNA. Not just similar molecules. Our DNA is made of an alphabet called nucleobases. And this team were the first people to realize that nucleobases are present in these rocks. They were present in that dust that we formed out of, the exact nucleobases of our DNA. So one of the last missions that I worked on, and it actually ended about a year ago in September, was something called the OSIRIS-REx mission, and that is an acronym, and I know it. Let's see if I can remember it. OSIRIS-REx, the Origins, Spectral Interpretation, Resource Identification, Security Regolith Explorer. Yes. Okay. Wow. So OSIRIS-REx was a relatively small mission, but it found something astounding, and that's what I'll end on. We went out to an asteroid that's about 250 million miles away. And our goal was to bring back a piece of this early solar system, a piece of unprocessed, unchemically changed building blocks of life. And this is the asteroid Bennu. It's about 0.5 kilometer across. And we went out there because it looked like it was dark as coal and covered with carbon and chemicals. And we actually had a big problem because we had designed the OSIRIS-REx spacecraft. I just want to show you this picture again. You'll notice that in this particular illustration, OSIRIS-REx is seen with a little vacuum cleaner, and it's picking up particles from a very nice, smooth asteroid surface to bring the particles back to Earth. When we got to the asteroid, as you can see there, it's starting to look very rocky. And as we got closer, it's even rockier. And we found out that the whole thing was covered with boulders. There was nowhere we could easily get down there with our little vacuum cleaner to suck up these samples. And so we scoured the entire asteroid, and we found out there were only a few spaces with sort of dust accumulating in little impact basins, little craters. And we had to reprogram the entire spacecraft. This is an artist's conception. But instead of a nice, smooth surface, we actually had to make the spacecraft autonomous. We had to teach it how to guide itself down. It was so far away that a light speed signal would take 20 minutes to get there, and then 20 minutes back. So as the spacecraft was coming down and saying, oops, I see a boulder's in the way, it'd be dead. We had to program on the fly, send up new commands, give it a new brain, and teach it how to navigate down between those boulders. So you can see here, one of the reasons scientists cheer so much is that a lot of times we're worried about things working. I was hosting this event. This is out at Lockheed Martin in Colorado. That's a real picture coming down with our vacuum cleaner. You also see some illustrations. And sure enough, we struck down, the vacuum worked, and we brought back this sample from the outer solar system of what the chemistry of our life is before the Earth even got started. It was during the pandemic, as you see there. And then after that, we began a 2.5-year journey back with this sample. Everyone's celebrating. We couldn't high-five each other because of the pandemic. We couldn't hug each other. So there's the sample being loaded up 250 million miles away, put in a little capsule. Here is last September over Utah, the capsule parachuting down. And there it is. There's a treasure trove of information about life billions of years ago in the building blocks. And to give you a sense how big it is, it's not very big. It's about the size of a microwave oven. So this is my last little video, but I hope it shows you a bit about how amazed we are at our connections to larger things, the stars and the galaxies. And I'll end on this.
The origin of life is one of the deepest mysteries in science, but the clues to solving it have been buried by plate tectonics, the water cycle, and even life itself. For answers, scientists are looking beyond Earth to primitive asteroids like Bennu, the target of NASA's daring OSIRIS-REx sample return mission. Now, material from Bennu is revealing a lost world from the dawn of the solar system, with the right conditions to foster the building blocks of life. When scientists examined the Bennu samples, they discovered evidence of a wet and salty past. Among the dark rocks were bright veins of salts that form on Earth when brines evaporate from alkaline lakes. Searles Lake, California is home to a mineral called trona, which is mined as a source of baking soda. Scientists found microcrystals of trona and other evaporite minerals within the Bennu samples, indicating that they once held pockets of sodium-rich water. Such brines are ideal for cooking up organic molecules, carbon-based compounds that are the stuff of life. Bennu is a carbon-rich asteroid, and its samples are chock full of organics, including amino acids and nucleobases. Amino acids can be bonded together in long chains to build proteins, which give cells their structure and function. Life is constructed from a set of 20 amino acids, 14 of which were identified within the Bennu samples. Nucleobases are the genetic components of DNA and RNA. All 5 nucleobases were discovered in the Bennu samples, a first for extraterrestrial material collected by a spacecraft. In addition to organic molecules, scientists found that the Bennu samples are surprisingly rich in ammonia. On Earth, ammonia is a common agricultural fertilizer. It readily evaporates at room temperature, but is more stable in cold environments, like those found in the outer solar system. Bennu is too close to the Sun to retain pure ammonia, so its samples must have formed during a more distant, frigid past. Salts, organics, ammonia. Thanks to OSIRIS-REx, we can now piece together these clues to tell a likely origin story for asteroid Bennu.
I'm going to have to stop it there, but one of the things that I just think is so incredible and beautiful, when you think about those stellar clouds and all of these beautiful, the dust, the carbon, the chemistry that's generated there, and then we fly through those clouds every single day. The asteroids, we now find the water in asteroids, we find the organics in asteroids is almost identical to what is in our bodies. And we don't think that's a coincidence. We think that's where these chemicals came from. The deep space, the stars, all around the galaxy, we accumulate this. We bring it to a stable environment like the Earth, where things can soak in water for millions and billions of years. And so we don't think it's just a coincidence that our DNA is based on things that you find very commonly in the asteroids and in space. So from NASA, everything from dealing with Earth science and very practical matters to asking questions about where did we come from and what is the story of creation. It's something I've had a huge honor in being part of, as I mentioned, for 27 years. And thank you so much for giving me a chance to share a little bit today. Thank you so much. If you have any questions, I'm happy to answer any. Yes.
Is it on? Okay. Time for 1 or 2 questions, and one came in from our virtual audience. So I'm going to start with that with Bob Poussant. How does NASA view SpaceX, and what is the relationship like?
Sure. I will say before that I understand that many of you are busy, so please, there's absolutely no offense to go in and leave. I am here. I can answer questions for as long as you like. I've got nothing else this afternoon, so please feel free to come and go. So SpaceX, for the longest time, the relationship with SpaceX has been extremely close because NASA has purchased our rockets commercially since the beginning of NASA. In some cases, NASA has been involved in making and building actual rockets, but for the most part, we do that with contractors. So Boeing, for example, built our Delta series of rockets. We also are working with Blue Origins on their New Glenn and New Shepard. SpaceX was commissioned by the government in terms of given funding. I mean, so SpaceX has been given about $34 billion of federal funding, taxpayer funding, to develop rockets for the use of NASA and also commercial space entities. And so they build very good rockets. And the Falcon series of rockets, OSIRIS-REx went up on a Falcon. I was there. I got to see the landing of the first stage, which is amazing. It's a 10-story building that comes flying out of the sky. Then the rocket fires and just sets itself down. It's unbelievable. So SpaceX has been involved as a government contractor with NASA for decades. They were 7 years behind their contract to give us a human-safe rocket to get to the space station and back, but they did. And then the Falcon series has done very well. So, we work with all kinds of private companies. Most of the funding that goes into NASA goes out to contracting companies to develop instrumentation or rockets or to universities. Most of the people that lead NASA programs like OSIRIS-REx is led by a professor scientifically. The team is the University of Arizona. And then the science team is actually all over the world. So SpaceX was a very good collaborator. We did not expect the politics to get this complicated. And one of the things that I've had trouble in the last decade is in some cases of Elon Musk's characterization of the company as something other than a government contractor funded by government taxpayer money. Yes.
Thank you. And I think we only have time for one more question.
I'll be around.
And then everybody else is going to.
That's right. For those of you that have questions, I'm going to stick around. So if you don't have time to answer on the microphone, you'll have time to catch me later.
Hi, Michelle. My name is John Ward. I'm a retired Foreign Service officer with the U.S. Department of State.
Hey, wonderful.
So great to have another retiree.
GS. Yay, that's right.
Exactly. And I had the great privilege to actually plan outreach events for visiting NASA scientists in India and a few other countries. So, one, thank you for your service and for the service of your colleagues. And as you might imagine, I'm watching things develop in the federal government with some level of horror. And I think you asked us to ask you
sure.
about what you think is about what's happening at NASA right now.
Yeah, it's been a really hard time. So the big thing that happened a couple weeks ago, which happened to pretty much all federal agencies, is they forced us to fire all of our probationary hires. So when you become a federal servant, kind of like getting tenure at a university, there's a 3-year probationary period, and then they decide whether they're going to make you permanent or not. For one thing, they've been firing permanent employees, which I didn't think was possible. I retired as a GS-15, and I was told that without due cause. I've served proudly under Democratic and Republican administrations. To me, it's about the facts. I came to be a scientist. So the probationary hire is all of our last 3 years of the best people. All of our new equivalent professors. Not only that, people that accepted a promotion or a different job that have been at NASA for decades. One of my friends is a heroic scientist. She's incredible. She was actually in Antarctica because she'd accepted a promotion. And they told her to leave within 3 days. She was in the middle of Antarctica. So the cruelty, the lack of respect of civil service, and people. I work with the best people in the world, and they do not get rich. The joy and the companionship and the humor and the fun and the hard work we do is something. I sleep well at night. I think integrity is still something that is actually really worth having in a life. And to see these people treated like that. There are layers of any big administration and bureaucracy like NASA where I think that they could probably remove 3 layers of it and everything would be fine. That happens mainly outside of agencies. You know this. So at NASA, for example, doing the communication, we would get a request from the Office of Management and Budget, part of the executive branch of the White House. And they'd say, well, you're spending billions of dollars of taxpayer money. It must all be evaluated and tracked. You must be vetted. You must have people do studies about whether this is working or not. And so we do. And that's a request from other parts of the government. NASA itself doesn't go and say, please give us more oversight. Please let us write more reports. But the reports are requested. And so that comes up to respond to this. I think a lot of that could be reduced. I really do. With very minimal impact on science. But the thing that was just kind of frightening is that this didn't go after any kind of real logical reduction. It's like get rid of all your best and brightest people, and I think illegally. And because people on probation, they were officially fired because of some sort of substandard service, which wasn't the case. So, this is going to play out in the courts, and I'm really sorry about that. But the disruption to people's lives and to young people considering a career in federal science, where the next administration can just fire you like that. That wasn't part of me signing on to my career. I did actually take an oath to the Constitution, and I thought that I could not be just politically gotten rid of. And so whether that is legal, whether that will stand, and what this will do to federal science, NASA's wonderful. I'm more worried about the National Institutes of Health and the Center for Disease Control. I think those are things that are going to impact people's lives faster than this will. So, no, I'll be honest with you. It's a scary, angering time. Yeah. As I said, I'm happy to stay and answer questions. I'll be around, so no hurry.